This is LC 131, Circuit Analysis 1, and this presentation is on band pass and band stop filters. So in the circuit of Figure 1, we see an example of a band pass filter implemented with a series LC combination. C1 is in series with L1. Now, hopefully you recall from our discussion of series LC circuits that at resonance, the impedance of this series LC combination is minimal. That at resonance, X sub C and X sub L are equal in magnitude, yet 180 degrees apart, and therefore they cancel. So at resonance, the impedance of this circuit, it will be at its minimum. The impedance of the circuit at resonance is just the series combination of RS, RW, and R load. And of course at resonance, if impedance is minimum, then current will be maximum. Therefore the output voltage, the voltage across the load resistor, will be at its maximum. Now at frequencies below resonance, X sub C is greater than X sub L, and the impedance increases as shown in the plot of Figure 2. Therefore, if impedance increases, current will decrease, and subsequently the output voltage will decrease also. And above resonance, X sub L is greater than X sub C, and again impedance increases as shown in Figure 2. And if impedance increases, the current will decrease and the resulting output voltage will decrease as well. So this is the action of the band pass filter. It passes a selected band of frequencies to the load and blocks frequencies below and above that selected frequency. The resonant frequency of the circuit of Figure 1 is, as shown, 10.7 kilohertz. Now, when discussing band pass filters, one of our concerns is, of course, is the loaded quality factor of the filter. And the loaded quality factor, signified with Q sub L, is determined by the relationship between the inductive reactance and the resistance that is seen by the inductor. Mathematically, the loaded Q factor of this series LC filter is X sub L divided by the Thevenin resistance as seen by the inductor. In the case of the circuit of Figure 1, RS plus RW plus R load. And X sub L is calculated at the resonant frequency. Now in the circuit of Figure 1, RS is the source resistance and RW is the wire resistance or the winding resistance of the inductor. Now don't confuse this loaded Q factor, Q sub L, with the quality factor of the inductor itself. You recall that the quality factor of an inductor is X sub L divided by RW. Now, the quality factor really gives us a quantitative way of assessing the selectivity of a band pass filter, where the bandwidth is calculated by taking FR, the resonant frequency, divided by the loaded Q factor. So the greater the Q factor, the smaller the bandwidth, and the more selective the filter is. So let's go through the analysis to determine the bandwidth of the circuit of Figure 1. So the loaded Q factor, X sub L, divided by the series combination of RS, RW, and R load is 5.17. And note, of course, this is unitless because mathematically we're dividing ohms by ohms. The bandwidth of the circuit is the resonant frequency, 10.7 kilohertz, divided by the Q factor 5.17, which gives us a bandwidth of 2.07 kilohertz. And we can approximate F1 and F2 by taking FR minus bandwidth divided by 2 to find the lower cutoff frequency, 9.67 kilohertz, and FR plus bandwidth divided by 2 to find the upper cutoff frequency, 11.7 kilohertz. And the Bode plot for the bandpass filter of figure 1 is shown in figure 3. Now we'll look at the analysis to determine or calculate V out for the circuit of figure 1. And of course, again at resonance, X sub L and X sub C cancel, and the only opposition to current in the circuit is the series combination of RS, RW, and R load. So the current in the circuit at resonance is 769 microamps. And the output voltage can be calculated either by using Ohm's law, I times R load, or the voltage divider formula, V source times R load divided by R total. Either method gives us an output voltage at resonance of 462 millivolts. Now at the lower cutoff frequency, 9.67 kilohertz, the output has dropped by 3 decibels. So the output voltage will be the maximum output voltage times 10 raised to the negative 3 divided by 20 power, or 327 millivolts. And likewise at the upper cutoff frequency, 11.7 kilohertz, the output has dropped to 327 millivolts. Now we can also implement a bandpass filter with a parallel LC combination as shown in the circuit of figure 4. Now recall from our discussion of parallel LC circuits that at resonance the impedance of the parallel LC combination is maximum. And of course this is because at resonance IC and IL are equal in magnitude yet 180 degrees apart, so these currents cancel. So at resonance current does not flow through the capacitive or inductive branches, current only flows through the load resistor. Now at frequencies below resonance, IL is greater than IC, therefore current has another path to flow than through the load resistor. And of course, if we look into the circuit of figure 5, we see that at frequencies below resonance, the impedance of the LC parallel combination decreases. Therefore, again, current flows to ground through the inductive branch, reducing the current through the load resistor. And of course, at frequencies above resonance, IC is greater than IL. And if we look at the plot of figure 5, we see that the impedance of the parallel LC combination decreases. And again, at frequencies above resonance, we have current flowing through the capacitor, therefore reducing the current that flows through the load resistor. And of course, the output voltage will decrease. The resonant frequency of the circuit of figure 4 is, as shown, 10.7 kilohertz. Now, the problem with the analysis of the circuit of figure 4 is that in the inductive branch we really have a RL circuit. We have the 100 ohms of wire resistance in series with the 10 millihenry inductor. And what this does is it causes the current through this branch to be at some phase angle other than negative 90 degrees. Again, the impedance of this branch is the sum of X sub L and RW. So therefore the impedance of the branch, of the inductive branch, is at some phase angle other than positive 90 degrees, as shown in figure 6. And of course, this causes the current through that branch to be at some current other than negative 90 degrees, as shown in figure 7. Because IC and IL are not 180 degrees apart, they do not cancel. And the analysis of this circuit would be difficult at best. So we need to have a means of making the wire resistance 0 ohms, therefore IC and IL will cancel at resonance. And we can do this by converting the series wire resistance to a parallel resistor. And if I can do that, then of course now IC and IL will be 180 degrees apart, therefore canceling at resonance. And we see this accomplished in the circuit of figure 8. I've taken the 100 ohms of wire resistance that was in series with L1 and placed it in parallel with L1. Now we have a purely capacitive branch in parallel with a purely inductive branch. Now mathematically this is accomplished by first finding the Q of the inductor, which you recall is X sub L divided by RW, and X sub L is calculated at the resonant frequency. So the quality factor Q of the inductor is 6.72. And the value of the parallel resistor equals Q squared times RW. So the value of the parallel resistor for the circuit of figure 8 is 4.52 kiloohms. And again, what this has accomplished is it gives us a purely capacitive branch in parallel with a purely inductive branch. So now these two currents will cancel at resonance. Now, as with our previous bandpass filter circuit, our analysis begins with finding the loaded Q factor of the filter. And again, the loaded Q factor is the relationship between X sub L and the resistance as seen by the inductor. And in the circuit of figure 8, the inductor sees RS, RP, and R load in parallel. So the loaded Q of that circuit of figure 8 is 1.80 as shown. RS in parallel with RP in parallel with R load divided by X sub L. And again, X sub L is calculated at the resonant frequency. The bandwidth of the circuit of figure 4 is 5.94 kilohertz as shown. The bandwidth is the resonant frequency divided by the Q factor of the filter. And with the bandwidth, we can now calculate the cutoff frequencies of the filter. The lower cutoff frequency is 7.73 kilohertz, and the upper cutoff frequency is 13.7 kilohertz. And the Bode plot for the bandpass filter of figure 8 is shown in figure 9. Now we look at the analysis of this bandpass circuit, and again at resonance IC and IL cancel, therefore the current supplied by the source is V source divided by R source in series with the parallel combination of RP and R load. So the source current is 192 microamps. And again, at resonance, the output voltage equals I times the parallel combination of RP and R load, 367 millivolts. And we can also calculate the output voltage using the voltage divider formula for the series parallel circuit in figure 8, where Vout equals V source times the parallel combination of RP and R load divided by the total resistance of the series parallel circuit, again 367 millivolts. And the voltages, the output voltage at the lower and upper cutoff frequency can be calculated by taking Vout max times 10 raised to the negative 3 divided by 20 power, 260 millivolts for the output at F1, 7.73 kilohertz, and F2, 13.7 kilohertz. Now we look at band stop filters. And we see an example of a band stop filter implemented with the series LC combination of C1 and L1 as shown in figure 11. Now again, figure 12 shows us the plot of impedance as a function of frequency for a series LC combination. And again, at resonance, X sub L and X sub C are equal in magnitude and 180 degrees apart, therefore they cancel. So at resonance, the impedance of the LC branch is RW only. So at resonance, of course, our load is in parallel with only RW, and again at resonance, V out will be at its minimum. There'll be a lot of current flowing through the LC branch, so the majority of the current is going to flow this way because the opposition to current is only 100 ohms. Therefore, the majority of the voltage is dropped across RS, making V out at its minimum. Excuse me. Now, at frequencies below resonance, X sub C becomes greater than X sub L and the impedance increases. Therefore, the circuit finds an easier path through R load than through the LC branch, and the output voltage will increase. And at frequencies above resonance, X sub L is greater than X sub C. The impedance of the LC combination increases. Therefore, current finds an easier path through the load resistor, and of course, the output voltage will increase. And the resonant frequency of the circuit of figure 11 is 10.7 kilohertz. Now we look at the analysis of the filter circuit of figure 10. And again, the loaded Q factor is the relationship between X sub L and the resistance as seen by the inductor. And the inductor sees RW, the wire resistance, in series with the parallel combination of RS and R load. So the loaded Q factor of the circuit of figure 11 is mathematically X sub L divided by RW plus RS and R load in parallel. So the band stop filter of figure 10 has a loaded Q factor of 3.84. And this gives us a bandwidth of 2.79 kilohertz as shown. And the lower and upper cutoff frequencies are calculated at 9.31 kilohertz and 12.1 kilohertz as shown in figure 12 in the Bode plot. Now I do want to point out here that notice the depth of what we call the notch in this circuit. The depth of the notch is negative 25 dB, which tells us that we have a very large attenuation of frequencies of energy, or attenuation of the signal at the resonant frequency 10.7 kilohertz. So this is a very selective filter in terms of a narrow bandwidth and a very large or a very high notch depth, negative 25 dB. Now we can also implement a band stop filter with a parallel LC combination. So we see in the circuit of figure 13 a capacitor C1 in parallel with an inductor L1, and of course L1 is in series with its wire resistance RW of 100 ohms. Now figure 14 shows us the plot of the parallel LC impedance as a function of frequency, and you recall that at resonance the parallel LC impedance is at its maximum. Again, at resonance, IC and IL are equal in magnitude and opposite in direction. So at resonance, no current flows through the parallel LC combination to the load. Therefore, at resonance, the output voltage will be at its minimum because the current that flows through the load resistor will be at its minimum also. Now at frequencies below resonance, IL is now greater than IC, and we have more current flowing through the load resistor. Therefore, the output voltage will increase. And above resonance, the capacitive current is greater than the inductive current. Therefore, the load current increases, and subsequently the output voltage will increase. The resonant frequency of the circuit of figure 13 is 10.7 kilohertz. Now, just like we saw with the parallel LC band-pass filter, the problem with the circuit of figure 13 is the fact that the inductive branch will not have a current at negative 90 degrees because that branch has an impedance that is less than negative 90 degrees. So we have to take the wire resistance RW that was in series with L1 and convert it to a parallel resistor RP as shown in figure 15. This way IC and IL will be 180 degrees apart, and they will cancel at resonance. So as we did with the band pass filter, we first have to calculate the quality factor of the inductor, which is X sub L divided by RW. Again, X sub L is calculated at resonance, which gives us a Q factor for the inductor of 6.72. And the parallel resistor equals Q squared times RW, which gives us a parallel resistor value of 4.52 kiloohms. And the equivalent circuit again is shown in figure 15. Now, to calculate the bandwidth of the circuit, again we have to find the loaded Q factor of the filter circuit, and this is again done by finding the resistance as seen by the inductor. Now the inductor sees R source in parallel with R parallel, RP in parallel with R load. So the loaded Q factor is this parallel resistance divided by X sub L, which gives us a loaded Q factor for this circuit of 1.8. And the bandwidth of the filter circuit is 5.94 kilohertz. We can calculate the lower and upper cutoff frequencies as shown at 7.73 kilohertz and 13.7 kilohertz. Now, I do want to point out with this parallel LC band stop filter that the notch depth is only negative 4.5 decibels. So this filter circuit is not as selective or does not attenuate the signal at the resonant frequency as well as the series LC band stop filter. Now, a popular circuit configuration for implementing a band stop filter is with a twin T circuit, as shown in the figure figure 17. Now, this twin T filter, and of course it's called a twin T filter because the combination of C and R divided by 2 and R and 2C look like the letter T, so they refer to this as a twin T circuit. Now, this filter is implemented by putting a high pass filter in parallel with a low pass filter. So the circuit or the RC combination on top is a high pass filter. Again, at high frequencies, X sub C is small. There's a lot of current through the capacitors to the output. And the lower RC circuit is a low pass filter. Again, at high frequencies, the X sub C is small and current flows through the capacitor at ground. Therefore, no current flows through the second or the rightmost resistor to the output. So again, we have a low pass filter in parallel with a high pass filter. Now we look at this high pass filter, and the resistor R divided by 2 sees the two capacitors in parallel. And remember, parallel capacitors are additive. So the resistor R divided by 2 sees 2 times C, gives us a cutoff frequency for the high pass filter of 1 over 2 pi times R divided by 2 times 2C, which of course equals 1 over 2 pi RC. Now the low pass filter, with the low pass filter, the capacitor 2C sees R and R in parallel. And of course, two equal value resistors in parallel equals R divided by 2. So the cutoff frequency for the low pass filter is 1 over 2 pi times R divided by 2 times 2C, which again gives us 1 over 2 pi RC. So this twin T filter is designed so that both the low pass filter and the high pass filter will have the same cutoff frequency. And this will be the center frequency of the band pass filter. So for the filter circuit of figure 17, the center frequency is calculated by taking 1 over 2 pi RC, which gives us a value of 61.4 hertz. And the Bode plot for that filter circuit is shown in figure 18. Now, in order to determine F1 and F2, we have to do this graphically by looking at the Bode plot. So we find the point where the output signal drops to negative 3 dB, and then of course we graphically determine that value at 15 hertz. Then we also look at the Bode plot to determine where the signal again passes the negative 3 dB point, and we find that point is graphically 240 hertz. This gives us a bandwidth of 225 hertz. Is that correct? Yeah. So this filter has a Q factor of 3.75. But I do want to point out that if we look at the Bode plot, that this band stop filter has a notch depth of negative 43 dB. So we do have extremely good attenuation of the signal at the center frequency. Negative 43 dB is a little over a rejection rate of 100.